Hello, welcome back everybody. Today we are going to start on section 2.6 of our geometry course, and this time we are going to define a few terms. As I mentioned last time, we went over section 2.5, which will be all of this guy right here, postulate 2, postulate 3, and also the definition of between. So today we are going to look at section 2.6, which will cover all of these stuff right here. So sit back and, grab something to drink and get ready to see how this all works out then, hopefully, okay? So let's go ahead and begin. So I'm going to go ahead and scroll down to where we last left off, which was around here. So just to kind of recap, the last thing we talk about is the word between. What does it mean for point B to be between point A and point C? So we said that in order for some point to be in between two other ones, we have to first acknowledge that the 3 points are collinear, meaning that there is exactly one line that contains them. And also the equation over here, AB plus BC is equal to AC, is true about the length of each of the segments, that you can add them two up and then get the big one as a result. So here we are now going to go ahead and kind of play around with this a little bit. And here's a numerical example of how between actually works then. So you can see on the number line that I assigned A on -3, B is going to be on the number 5, and C is going to be 7 on the number line. So here we say that B is between A and C because, well, for one thing, we are on the number line, so that's why everything is okay. So there is a line that exists then. So since this is the number line, then that means that there exists exactly one line that contains them. So that first part is going to be checked off. Then the second part is I need to show that AB plus BC is equal to AC. So here, let me just go ahead and write that out. AB plus BC is equal to BC. So here you can see that AB, the length of it, is going to be equal to -3 minus 5 absolute value of it, and that's going to be equal to 8. Then from BC, that is going to be 7 minus 5, which is going to be equal to 2. And lastly, from A to C over here, that's going to be absolute value of 7 minus -3, which is going to be equal to 10. So definitely 8 plus 2 is equal to 10. So that means that checks out then. So as a result, because both of these things are verified, then therefore point B is in between A and C. So that's how we can kind of use this as like a proof. So let's go ahead and use this in part of our theorem over here then. Let's go ahead and try to see if we can prove this theorem. So here in theorem 2.3, this is what is known as the point plot theorem. So let's go ahead and let's see what it says then. Let A, B, and C be points on a line with the coordinates x, y, and z. So respectively, and I am told that if x is less than y is less than z, then the following is going to be true, which is going to be B is in between A and C. So first, let me just kind of draw a visual so you can see what this theorem is actually talking about. So here we can have, like, say, a number line then, okay? Now what I'm going to do is I'm going to go ahead and put out the following points. I am going to write it so that here we have A, and then here we have B, and then here we have C. So these are going to be point A, point B, and then point C. And the numerical value of it is going to be x, y, and z then. So let's say x over here is equal to 3. Let's say y over here is equal to 4. And let's say z over here is going to be equal to 7 then. So here you can see 3 and 4 and 7. So we are not necessarily going to have this order, but it could be the case of that order. But now here's the part that solidifies that order right here. So it says that x is supposedly less than y, is supposed to be less than z. So you can see how that actually works out in this case then. So you chose 3, 4, and 7, right? So all that condition is true. And the conclusion is that B is going to be in between A and C. So yeah, you can definitely see that in the picture then. Here, if you want, we can just go ahead and try one more time. So let's say x is equal to 100. And then let's say that y is going to be equal to 111. And then finally, z is going to be equal to 115 then. So on the number line here, you can have 100 right here, which is supposed to be denoted as A. And then we're next to it is going to be 111 on the number line, and that's going to be denoted as B. And finally, at point Z, which is, sorry, not point Z, but the numerical value of Z, which is at 115, so somewhere on to the right of it, that's going to be C. And once again, you can see that B is going to be in between the two then. All right, but there you go. That's what the theorem says. And now let's go ahead and see if we can prove it using what we know so far. Okay, so remember, what I need to do is I need to prove that B is in between A and C. So over here, I'm just going to write down what is it that I need to show. Well, according to what we've been saying so far, remember, if B is in between those numbers, if B is in between those 2 points, then that means that I need to show there is a line that is going to contain all of them. So here is going to be number 1. There exists a line that contains points A, B, and C. Okay, so that's the first condition. And then the second condition is that the next part is AB plus BC is equal to AC. So, oh, sorry, I think I just found another mistake over here that I made exactly the same as last time. This right here should say AC right there. So strike 2 for me on that one. Okay, so let's see if we can go ahead and prove this. Now, once again, for the first one, that's really easy because, again, we're going to be working on a number line, so that's why it's going to be okay. So this is actually done already, right? So here, there's nothing to do because, look, in our prompt, we are told that we are actually on a line. So that means that that part is checked off. So now we just have to prove that second part over here. Okay, so here's what we're going to do then. Let me go ahead and clear the board over here. So then that way we can go ahead and use some like variables so we can represent all of these guys. And let me go ahead and maybe use a bigger eraser in this case. All right. So here, let's go ahead and do the following. So on this number line, let's go ahead and say that X is going to be assigned over here. And then Y is going to be assigned over here. And then Z is going to be assigned over here because, again, remember, I know that it is in the order of the smallest to the largest. So hence from the left to the right. Now, in addition to that, we know that the points are supposed to be A over here and B over here and supposed to be C over here. So these are the numerical values, so numbers, and then these are the name of the points. Okay, so let's go ahead and start with each one then. Now, AB, the length of it, okay, AB, the length of it, if you remember, how do you find the distance between 2 points? Well, we take the absolute value of the difference of the number. So that means I'm going to have Y minus X in this case. Then I'm going to go ahead and solve for BC, and then I am going to have Z minus Y in this case. And finally, I am going to solve for AC, which is going to be then Z minus X in this case. So this is just basically using the same thing as what I did over here on the number line with the numerical values, but except I'm just using variables. Now, if you recall, there was a theorem in the last section that talks about, hey, you know what? We can go ahead and take one of the points and assign it 0. Okay, we can take any one of the point and assign it the number 0. So just to kind of help you remind you, that is over here what is known as postulate number 3, the ruler placement postulate. So what that means is I can go to my example. To make this a little bit easier, I'm going to go ahead and set this equal to 0. So literally meaning X is equal to 0. And if you're wondering, well, how is that going to help out and make things a little bit easier? Well, let's look into this case then. Over here, right? If I set X equal to 0, then that means that we just have the absolute value of Y, which is technically equal to Y, because remember, Y is to the right of 0, so therefore it is positive. Okay. Next, over here, that one is just going to be Z minus Y, because remember you have a Z value which is larger than Y. So then that means that this is just literally a bigger number minus a smaller number. So that is going to be equal to Z minus Y. Last thing, or for the last one, same thing, right? You see an X in there. So that means we can make this simple. We can go ahead and say that X is equal to 0 according to what we just said. So this now gives you absolute value of Z, which is equal to Z. Hey, look at that. Now we have some nice clean variables that we can see if we can set equal to each other. So finally, we're going to take all this guy and put it back into our equation and hope and cross our fingers that it is true then. So AB plus BC, is it equal to AC? Well, according to what I have, AB is equal to Y. And then we have BC is equal to Z minus Y. And then now the question is that equal to Z, which is equal to Z? If this equation right here is true, then that means we are done. And I definitely do think so, because Y minus Y is equal to just plain old Z. So Z is equal to Z, then that is going to be our proof then. Okay. All right, so that was the first, well, one of the first proofs that we did, and hopefully that was okay. A lot of these theorems and proofs, they're really, really minor and they don't really get used that often. But the time that we do use them is to basically be, is so that we can build it in order to create proofs that we are going to use, or sorry, it's going to be used so that it will create theorems that we can use in the future that are more useful, okay? All right, so next piece, let's go ahead and talk about theorem 2.4 over here then, okay? This one says that if you have points A, B, and C are going to be on a line, okay? Once again, they're just going to be points on a line, and it's not necessarily going to be B is in between the two. They said that then there is exactly one point in between the other 2 points. So here is the visual once again. So here's your line, right? And they're saying, hey, you know what? These 3 points are basically anywhere on the line. So they want you to show that there is exactly one of those points will be in between the other 2. Well, that's pretty hopefully straightforward to see how that works. One case would be, like we said, A is over here, C is over here, and then that means that B is over here. So in this scenario, you can see that B is in between A and C. But it could be also the case where maybe C is over here, and then A is over here, and then B is over here then. So in this case, we have C, A, B, right? And so, take one more example just in case. How about if we have maybe like say B is on the far left, and then we have C is on the far right, and then we have A in the middle. So in this case, we can say that A is in between C then, okay? But nonetheless, every single time you'll notice that there is exactly one point that is in between the other 2. Okay, so that's what they have done. So in terms of what is it that I need to show, I guess we can write out all the cases scenario. B is in between A and C. We can also have C is in between B and A. Then we can also have A is in between C. We can also have C is in between B and A. We can have, let's see, A is in between C and B. And finally, we can have B that is in between C and A. And wow, that is a lot of things that we need to show. Do we necessarily have to show all of that? The answer is no. There's actually like a really, really quick, simple trick that we can actually use to get out of this. Now, here is what we're going to do, okay? Anytime that you see the word exactly, that is what is known as a theorem, or a theorem or proof that shows uniqueness. Okay, that is a theorem or proof that shows uniqueness. Meaning, when I say uniqueness, that means that there exists exactly one and only one of what is it that I need to show. So in this case, I need to show that there is exactly one line, that there is exactly one point that is in between the other 2. Now, in terms of how do we show the proof for uniqueness, well, there's an easy way to do this actually without having to do all that extra work, okay? Why don't we assume the negation of that? Okay? And by that I mean, okay, if I'm trying to prove that there is exactly one point that is in between the other 2, then I'm going to go ahead and assume that there are more than one point between the other 2 points. Okay, Well, let's think about what this is saying. I need to assume that there are that there are more than 1 points between the other 2 points. Well, that is actually not possible because we're only given 3 points to work with, right? Technically, yes, there are infinite number of points in between any 2 points that are distinct, but because we're only working with the 3 points A, B, and C in this case, you can't actually have that, okay? You can't actually have that. So you can see how this indirect proof makes our life is a lot easier because instead of having to prove 6 things right here, we just go ahead and assume that this doesn't work or assume what we're trying to prove is not going to be able to happen. And what's going to happen in that case is that there's going to be a contradiction along the line. So over here, once again, let me just go ahead and state it then. Assume that there are more than 1 points between the other 2 points. This right here is a contradiction, and that's the symbol for contradiction, because we only have 3 points to work with, and 2 of them have to make up the endpoints. And so therefore, that's going to be our contradiction then. Okay, so a lot less work for this then. So we'll deal with the idea of this uniqueness proof in the future, and we'll definitely see more of that to kind of help us out then. But for the meantime, anytime that we want to show that there is exactly one of anything, always best case scenario is to do an indirect proof to show the uniqueness then. Use contradiction. Okay, let's go ahead and talk about postulate over number 4, and this one is called a lying postulate. Now remember, postulate is something that is very simple that you do not actually have to prove for because, well, there's really not that much to prove because it's just that basic then. So here is what it says. For every 2 distinct points, and by distinct point, I mean that they have to be different, meaning they're located in 2 different locations, they're not the same. There exists exactly one line that contains both. So here is point A, and then here is point B, and you can see, yeah, that's definitely true because there's only one line. Because, well, the line, if you're thinking, okay, well, what if I drew it something like this, and I drew it something like this? Well, those unfortunately are not lines because it's not straight then, okay? And if you're wondering, okay, well, can I do a indirect proof to actually show this? The answer is yes, but again, this is a postulate, so we're not going to do a proof for this one because it's actually so basic, we just kind of like, disregard it for the most part, okay? Okay, so let's now talk about how the segments and rays and lying and all that other stuff is related to all of this stuff, okay? So we're going to have to go ahead and define a few things to help us with our homework assignments. Here, you can see that I have set up 4 different definitions. We have segments, we have rays, we have lying, and we have opposite ray. And what's going to happen is we're really going to just define one of them, and then the others are going to be a build-off of the previous one to make things a lot easier. So here we go. Here's the first part. To define a segment, we say segment AB is defined by the union of all the points in between A and B. So segment AB is going to be the union of all the points that is going to be in between them. So here is what we're talking about. You have A, you have B, right? In order to draw a line, you definitely draw so that it looks something like this. And they're saying that by definition, the segment AB is basically all the points that makes up that line, right? And that's pretty straightforward for the most part. So anything in between over here, right? We are going to say that that is going to be any points in between AB. All the points in between are going to make up that line then. Okay. Now, ray for the second one, here is this going to be the following. Ray AB, and you'll note that there is a small little arrow above right there to indicate that it's a ray, is defined by the union of, now here, what I'll do is I'll take AB over here on top, and I'm going to go ahead and draw ray AB because, we know what that looks like. But the thing is, we want a formal definition to work off of. So here you can see that if I ask for ray AB, then it's the union of something and something else. Well, one thing that I notice in this picture is that it's going to contain AB, the segment. So then that means that I can go ahead and put that in as one part. So segment AB. And the next part, now that part is going to be a little bit tricky, okay? So here's what we're going to say. I'm going to go ahead and say that there's an arbitrary point x over there on the far right, okay? So the way I'm going to define it is that ray AB is going to be defined as the union of AB, the segment, and the set of all points x such that x is between, such that B is in between A and X. Okay, so let me go ahead and write that out. So, and the set of all points we'll go ahead and call X such that B is in between A and X. Okay, so you can see how any point that I pick on the right of B, B is going to be in between those 2 points. And remember, B being the point in between doesn't necessarily mean that AB is equal to BX. Okay, so it's just going to be some points. And yeah, that's going to be our ray then. So note how what we did was we built off our definition of segment in order to get ray. Now, finally, for the last one, which says line AB, right? And note that there are kind of like, rays of going in the opposite direction. That's how we define line. Is defined by the union of, well, let's go ahead and think about what we said about ray and also segment. Here, if I draw line AB, going back to my picture once again with this whole thing, line AB is the whole thing, right? Because it goes on forever, supposedly. The way I see it is that you have 2 rays that are connected together. So that's going to be the union that I'm looking at. So maybe I can say that AB, the line, is defined by the union of AB, the ray, going in one direction, and also BA, the ray, going in the opposite direction. And yes, the order actually does matter in this case, because you can see how in this first case, right, it's going towards B to the right-hand side, but whereas in this case, it's going towards A on the left-hand side. So those are going to be the sum of those 2 rays then, the union of those 2 rays, okay? So there it is. Now, speaking of which right there, notice how I use the term AB the ray and BA the ray. Those are what is known as opposite rays because they are pointing in the opposite direction, but yet they are on the same line. So here is going to be my final definition in this case, opposite rays. So if we know that A is in between B and C, the 2 points, then we can say that AB is going to be the opposite ray of AC, which is located over here, right? So looking at the ray of AB, that is now the opposite ray of AC because you can see that they're on the same line, but they're going in the opposite direction then. Okay, so that's how we define the opposite ray. All right, so we're almost there. Okay, here is the next theorem that we're going to be coming up with. And again, this one right here, the theorem 2.5, is going to be a very minor one. You're not going to see a lot of this one in a proof, but rather you're going to be using theorem 2.5 to prove something that is going to be pretty big that's coming up. Okay, so here it is, theorem 2.5. It says, let A be the ray, let AB be a ray, and X be a positive number. Then there exists exactly 1 point P on AB such that AP is equal to X. So here X is referring to a number. Okay, so here AP is kind of like a numerical value then. So here in this picture right here, you can see that we have AB, right, the ray, and they're saying that there is a point P on there somewhere, right? It could be in between AB, it could be after AB, but let's just go ahead and put it like over here, so that it's afterwards, such that there is a point on there. So then that means the length of this is going to be equal to X. Okay, now again, looking at the words that I noticed, I am going to try to prove that there is exactly 1 point so that there is going to be that length. Okay, so let me just kind of reiterate what this theorem is actually saying, just in case you're a little confused. Okay, so it says basically that, hey, you have a ray right here, AB, and on that ray, I am going to have a certain length. Okay, I'm going to have a certain length. Let's go ahead and call X then. So if I have a certain length that's going to be called X, we can only go to the right by that amount. And they're saying, hey, there's exactly 1 point on there so that that length AP is going to be that length of X. Okay. Now, as we said earlier, what I want to do is I'm going to go ahead and prove by contradiction. So then this is because this is a uniqueness proof. Assume that there is another point P, we'll go ahead and call, actually, assume that there's another point we'll call P prime such that AP prime is equal to X. So you notice what I did there was I basically said, hey, let's look at what we're trying not to prove and see if that actually works out. So I'm going to say that there's another point P prime, we'll call it that, such that the length is equal to X then, okay? Now, this unfortunately is not going to work because if you recall back, right, the point plot theorem, it basically says that I can assign A is equal to 0. And if I do assign A is equal to 0, then that means that P has to be a unique point. So that right there is going to be our contradiction. The only way for this right here to happen is if I drew another line over here, right? And point P would then have to be somewhere over here because, point P prime would have to be somewhere over here because then there will be two different lines in this case. Well, that right there is a contradiction, as you can see, right? Because we only have one line to actually work with, or one ray to actually work with then, okay? All right, so the last few things, and then I think that'll be it. So the next one is the definition of a midpoint. So this one, I think it should sound somewhat familiar. And the way we define a midpoint is that if B is considered the midpoint of AC, right? Let's go ahead and draw this out. We can kind of come up with a conclusion with all that. So here is maybe A on the left and then C on the right, not necessarily that way, but it could be like C and then B. B is supposed to be the midpoint. So let's think about length, right? Well, if it's terms of length, then that means that AB should be equal to BC. So that's going to be one part. So we can say AB, the length, is equal to BC, the length right here. Okay. Now, for those of you guys that are going, well, actually everybody's doing geometry right now. We can also denote it as the following. We can say segment AB is congruent to segment BC. Instead of saying that the lengths are the same, rather, I'm just going to say that the two lengths will have the same length, and that's another way of writing it. Just as it's a different notation, okay? The notation on the left basically means that their numerical values are the same, and the notation on the right is basically saying that, you know, it's basically just calling them by their actual names, segment AB and segment BC, but it still means the same thing, okay? Now, another equation that I could possibly write is 2AB is equal to AC, or we can also say 2BC is equal to AC. Okay, either one of those should be okay. Or you can even write it like this: AB is equal to 1/2 AC. Or we can say that BC is equal to 1/2 AC. So any one of those should be totally fine then in terms of definition. Now, one other thing that we probably kind of missed, but hopefully you didn't, maybe I did, is that B is going to be in between A and C right there. Okay, so anytime that somebody says, hey, B is the midpoint of the segment, then that means that you can extract these four information out of them. Okay, and a couple of small things over here just to kind of get you to get used to the notation. Whenever we say that you have bisect, the word right here, right? A midpoint bisects a segment. So what that means is that point B is going to cut that segment AC into half, and that's why we have equal length. So that's what it means to bisect then. It's to cut it in half. Now, the last part of this is that the bisector of AB is a line that contains the midpoint of AB, but is not AB itself. So then that means that if I have A over here and we have B over here, if I am going to say that there's something that bisects it, if there's a bisector of it, then that bisector is going to cut AB in half, so meaning it contains the midpoint over here, so that these two line segments are equal to each other. And these two little dash right here is to indicate that they have the same length. So here you can see that this line, we'll go ahead and call line L, is going to bisect AB because it contains C over here, which is the midpoint. All right, so here's the very last theorem of this one then. every segment has exactly one midpoint. Okay, every segment has exactly one midpoint. Well, let's go ahead and do it the easy way then. Okay, remember what we said, this is a uniqueness theorem. So that means that we want to prove using contradiction. So here we're going to assume that there are two midpoints and see exactly what's going to happen then. So let's say that we have segment AB. Okay, so let's say that we have segment AB over here. Okay, and then let's go ahead and say that C is a midpoint and also D is another midpoint. Okay, so over here, let me just go ahead and erase that. I'm going to assume that C is the midpoint of AB. Okay, and at the same time, D is the midpoint of AB. Okay, now with that assumption being made, then let's go ahead and go up to how we define a midpoint and see if we can play around with it a little bit. Okay, one thing I can do is extract it over here and say that since that C is the midpoint, then I know that C is in between A and B. And then for this one, I can say that D is in between A and B. Okay, not much to play with. But if I take maybe like say the second part of it, then I have something to actually play with. Because if you notice the first piece over here, what I can say is that by the definition of midpoint, okay, then that means that AC, right, is equal to CB, and AD is equal to DB. Okay, so using one of those three equations that we have, then we can definitely say that that's equal. That's going to be true. Or if you want, we can actually look at the whole segment, and I think that might actually give us something to work with. Or we can say that AB, the entire length, half of it is equal to AC. Okay, and then in the other case, we can say that half of AB is then equal to AD. Okay, well, I think that part right there is going to kind of give us what we want. Because if you now think back by the point plot theorem, okay, if you think back to the point plot theorem, in order for this right here, in order for this equation to be true, right, the point plot theorem says that, hey, I can only assign one single point to each of the value then, okay? What I'm referring to is basically this theorem 2.5 that we just talked about. Let AB be an array and X be a positive number. Then there is exactly one point P such that AB is going to be equal to X then. Okay, so what I did was I basically said, hey, let's go ahead and use theorem 2.5, apply theorem 2.5 to this then. Okay, and unfortunately we cannot apply theorem 2.5 because as soon as we do, we realize that point C is the same thing as point D. Okay, so we can say that this right here, then therefore, that's the symbol for therefore, okay? Point C is equal to point D by theorem 2.2-5 because there is exactly one point that is going to make this true. And that right there is going to be our contradiction because remember, we assumed that those two were distinct points to begin with.